Hey everybody, and welcome back to Calc 3 Online. So today is a big day because we get to talk about something called a partial derivative, which is a very important thing in Calc 3 and tons of other courses. It's basically the multivariable definition of a derivative. And after this, there's kind of another really big day where we'll eventually see like the multivariable definition of an integral, which is really just an integral inside of an integral. But those two are like the big kind of concepts that you definitely want to make sure you understand leaving Calc 3. And one of them is you're going to learn about today. But to get going, I just want to basically do another limit problem, and one that uses the squeeze theorem. So these are like a little trickier because you have to kind of figure out those boundary functions in order to solve it. So the way I would start this one off, so we know that if we did like, y squared over y squared, except for when y is 0, this would be like equal to 1, right? And so if we add some more stuff to the bottom of it, right, like add x to the fourth, then that thing should be less than or equal to 1, right? Because now it's like a fraction, like 1/2 or 1/3 or something like that. And all these numbers are even powers. And so we also know that, for real values, this thing is going to be greater than or equal to 0. So basically, I'm just trying to build this thing up. And I could next just like multiply everything by this 1 minus cosine 2x term. And so if I do that, I would have, I'm just going to do it like this. So I would have 0 less than or equal to y squared over x to the fourth plus y squared times that 1 minus cosine 2x, and then that's going to be less than or equal to, 1 times 1 minus cosine 2x. So then, and this is okay to do because it's not going to like change any signs. I think that's important to say too, because like I'm not going to have to flip this because I didn't multiply by a negative, because cosine is at most 1, right? And so really 1 minus 1, this thing's 0. If this is negative, then this is like a bigger positive number, right? Because it's going to be a double negative in there. So I don't need to flip signs or anything because I'm just multiplying by a positive number. And now this is where the squeeze theorem comes in. So, the limit as x and y approach the origin of 0 is equal to the limit as xy approaches the origin for 1 minus cosine 2x, right? Because if you plug in 0 right here, right, then you're going to get 1 minus 1, and that's 0. And the limit of 0 is definitely 0. So these two, like boundary functions, both go to 0. And so then you can conclude the limit of the big messy thing. Whoops. The big messy scary thing here. That this also has to go to 0 just by the squeeze theorem. And that's it. So, this one I think is a little bit trickier because you have to like see this fraction idea to kind of get going. But if you just think, this part right here, y squared over y squared would be 1. So if you add more things, positive things on the bottom, now you've got like some fraction between 0 and 1, right? And then you can just multiply by this because it's a positive number. It's not going to flip any signs or anything. And that's a nice limit, and that's a nice limit. So then this is squeezed between the two, and it has to have the same value at the origin. All right. So Partial derivatives. So basically the idea is similar to Calc 1, so I want to make sure we kind of start there. So the idea of a partial derivative still comes out of limits. So both integrals and derivatives are limit-based operators. And in Calc 1, the idea is like you take some secant line here, and all you're doing with the limit is you're limiting the distance between this point and this point to be really, really, really small, right? Like, let's say this is the point I'm moving in. So, I could get another secant line that's right there, and then I could move another point here, and I could get another one right there. And like, as I bring this point in, I'm getting really close. Maybe I should do this one in a different color. I'm getting really close to that tangent line. And that tangent line, is an approximation of the slope of the curve at a point. That's all we're doing when we do a derivative. We're just, that could write down the limit definition, but, it's just the, delta x is approaching 0, and the delta x is just your, this is like your change in x, and you're basically just bringing, from this point, you're just bringing this one in closer and closer and closer until that delta x is basically 0. So that's the idea in 2D, right? And in higher dimensions, it is very similar. Honestly, the only difference is what I kind of write up here. So for multivariable functions, just like with limits, when it comes to derivatives, there are just many more paths to consider for the surface. So there's lots and lots of tangent lines that we could draw, for some sort of surface here. I have this point, let's say, and I could find a derivative, along like a diagonal like this. I could find one that kind of goes like this. There's actually a notion of finding a derivative in all these different directions, and that is what we call a directional derivative. The two that we typically start with, and just make sure that we understand really well before we move on, are the derivatives in two very special directions. So this is where the idea of a partial derivative comes in, because we're going to be looking at the derivative just in one kind of part or direction of the surface. And the two that make the most sense to kind of check are in x, which this line right here is like parallel to the x-axis, and in y. So you've got some sort of, curve, C2 in the y direction, and we could find like a tangent line to that curve, just like we'd found a tangent line to a curve over here. But we could also have like a curve in the x direction that passes through that point and find a tangent line along that curve. Okay. And this is, I'm going to actually show you other ways that we write them, but this is actually proper ways to write partial derivatives of the function with respect to x or y. So we would read this as, the partial of f with respect to x at AB, and this is the partial of f with respect to y at AB. And they are truly just the slopes of tangent lines at that point along, here perpendicular planes, x equals a and y equals b. And you're going to see this very soon, but another way that we actually write this is this weird, instead of like d dx, that's like what we call the total derivative actually. So that's just like a function of just one input. So if, as a way to represent that there's many different directions, we use kind of a weird curvy d, and this is actually just called the partial symbol. But I wanted to talk about this question right here. So let's say you're asked, what is the rate of change in y along curve 1? Okay, so curve 1 is this curve right here. And if I asked you to find the partial with respect to x of y, though, along that curve, you would have to say 0, because there is no change in the y value, right? Like at this. The only way you can change the x value is if you're on this curve and then you took like a hard right turn and you just moved it over there, or a hard left turn and you moved over there. But along this curve right here, there's no change in y. It's just changing in x, right? So you can also do things like you can say partial with respect to y of anything that's just x, that is 0. You can do things like partial of z with respect to x again, let's say, that would also be 0. Like anything where this is basically just treated as a constant in terms of the z direction. X is constant in the y direction. Y is constant in the x direction, right? There's like, let's just say, for argument's sake, let's say this is like 2 in the y, right? Along this curve, the y value is just always 2. Like it's just projected right over, that y equals 2 right there. So that's an important kind of partial derivative idea that I want to make sure you understand. So these are just all the different ways that we actually write them. So the big ones are kind of these first few right here, I guess. This one I don't use too much, and this one I don't use too much. But and also, actually, I don't use the F1 and the F2. Actually, I'm going to erase these so you can still see them. But I don't use these later few too often. But these first ones you're going to see me use a fair amount. So if you have like z equals f of x, y, we could say, this one and this one are basically saying the same thing, except partial of f with respect to x, whereas partial of z with respect to x. But it's like f of x is y. It's like that idea. You could write the function this way, and it's like this is operating on the whole function, right? Sometimes we don't write the f sub x of xy part. We just drop that. We just write f sub x. This weird little partial symbol is what I was trying to draw on the last page. And, you could do all of those here for y. And they're just, checking derivatives along, the x direction, like parallel with the x-axis or parallel with the y. But you should definitely feel comfy kind of with all of these. You're going to see all of them at some point. All right. I just want to kind of start sort of simple here. So if you have this function, I want you to find the partial of x with respect to at the point 1, 1, and then the partial of y at the point 1, 1. And I want you to kind of think of these in terms of slopes. And so I'll kind of reference these pictures here in a second. So if you were going to do the partial of this function with respect to x, right, the derivative of a constant is always just going to be 0. So that's still just 0. The derivative of the x stuff, it's just a normal derivative with the x stuff. So we literally just have now negative 2x. And then just like before, this thing, y is not changing in the x direction. It's constant. So the derivative of a constant is 0. So this part also goes to 0 when we do the partial with respect to x. So that's literally all we get for the partial of f with respect to x. So then if you do f with respect to x at 1, 1, then you just get negative 2, right? And that agrees with what we have down here. So this line right here has a slope of, that's how we understand this, has a slope of negative 2. It's going like downhill, right? as you kind of go up in x and stuff like that. And likewise for the other one, if you do the partial with respect to y, the 4 is constant, that derivative is 0. Now the x is constant with respect to y, so that's 0. So then you just get minus 4y. It's just the normal derivative with y. So then if you plug in 1, 1, you get negative 4. And that is, this line is supposed to be a little steeper than this. Basically, it's negative 4 here instead of negative 2. But yeah, that line is truly has a slope of negative 4. And yeah, you can see, I kind of like this dotted line here to kind of remind you, the x is constant. And so since the x is constant, right, you're not going to, when you take the derivative of the x with the y one, you're going to just get like a 0 there. All right. So just kind of messier, but just, I guess, a messier example. No slopes or anything work its way in here. So I want the partial of this function with respect to x and y. This is just a good one to kind of get you guys used to like seeing how like chain rule would pop up and stuff like that. So if we did the partial of f with respect to x, the inside of the trig function has x's and y's. So I will have to do like the derivative of the outer function first. So the derivative of sine is cosine, right? And then just copy all this, just like normal chain rule. And then you just multiply by the derivative of the inside, but you have to remember that it's just in terms of x. So the derivative of this thing with respect to x would be like 2x, and then this is constant, so we just sort of tag it along. Then we have minus 2, right? The derivative of that, and that's derivative is 0. The y is fine there, basically this I just think of as like, if I had asked you what's the derivative of, let's line it up even more like it. So say it was like x squared times 4, which you wouldn't write that way. You would just do 2 times x times 4, and there you would multiply and you'd get 8x, right? But that's exactly what I'm doing here. The y is just like a constant, like the 4 is. That's all I'm trying to say. So we just tag it along. And it doesn't simplify anymore. You just literally write it that way. You can just do that. And then partial of the function with respect to y is going to still start off with a cosine, right? And then you have to copy everything. And then chain rule, you just multiply by the derivative of the inside. And here, this is in terms of x, so that'll be derivative of that with respect to y is 0. That has a 0 derivative with respect to y. So this is the only thing that you're basically really taking the derivative of. That's like non-trivial inside. And you would just get x squared. Because like this is, to me it looks like, again, some sort of constant like a 4 times y. And we know when we do d dy of that, we get 4. And so this thing, the 4 is the x squared. That's like the constant here. All right, fix that. And we can actually do like second order derivatives and things like that too. I actually have a whole nother day planned for that, but just to kind of give you the idea of it now, we are going to see these very soon. So you can actually do things like this. You can do like partial of f with respect to x, let's say, and then, this function up here had y things in it, and maybe for some reason you want to, after that, take the partial of it with respect to y. So the way we would actually write this is, just like if you take a second derivative, you say like d squared over dx squared. Now here, it's not dx times dx, so you don't say dx squared, like the quantity squared. But here you would write like partial squared of f, and then partial y, partial x. But you can also do things like take the partial with respect to x after you took the partial with respect to x, right? And then here you would say partial squared of f, right? With respect to, I'm just squaring the bottom. So partial of x squared. This is really just like when you do like, d squared, dx squared, like second derivative. So you'll see these. These are called just higher order partials. And they can get kind of weird and messy. But there's nothing wrong about taking these functions and taking derivatives with respect to like y, like after you did an x, or x again after you did one with x, that kind of thing. All right, so the last thing I want to do is, this is basically an implicit derivative problem. So hopefully you kind of remember how implicit derivatives work in BC and stuff. It's pretty similar here, honestly. And there's actually going to eventually be a shortcut I'm going to show you to kind of do these even quicker. But just as like a quick, recap over here. So implicit functions are things like circles are perfect examples. Like they're basically just functions you can't solve for y explicitly. So the best you can do here is you can say y equals plus or minus the square root of 1 minus x squared. But since there's like two different things, it is not explicitly a y equals function. So this is an implicit thing. And this is implicit, but now you have just 3 variables instead of 2 variables. So I want the partial of z, like the function, with respect to x, okay? So I'm basically just going to go through and take partial of everything with respect to x. And when we get to something with z, we'll talk about it because then it's a little different. But the first one right here, pretty straightforward. You're just going to get 3x squared, which is a normal derivative with respect to x. This is nice because it has no function of x, so that derivative is 0, okay? So maybe I'll even kind of just say it goes to 0. Now, z, let me actually also do something kind of off to the side here. So z is like a function of x and y, right? And since z is defined in terms of x and y, it's implied, it's like there's an implicit piece here, that there is some sort of x in that right there. Like this z has some sort of x part to it. And so when we take the derivative of z, we have to sort of assume that there's like a chain rule going on. Like it would be like the, function is a cosine with some x thing inside of it like this. So the way we deal with this is we just do the derivative of z like normal, so 3z squared. But then we need to multiply by the partial of z with respect to x. This is the implicit idea. This is like you do this kind of thing with BC and stuff. So this is where I'm accounting for it's like the chain rule. That's all I'm doing. And then I think I'm going to need a little more room. So I'm going to get rid of this. So then this is a product rule because you have you can group it you can group it, I guess, a few ways. Let's group it as like a 6xy and then a z. So, this z is a function of x and this is a function of x. So when I take the partial of 6xy with respect to x, I get 6y. And then product rule, you have to multiply by the other function, so z, right? And then you add let's see, it'll be the 6x y is the first function. And then I just multiply it by the derivative of z, which is just partial of z with respect to x. And then the derivative of 1 is 0. So just to kind of recap, all of this is product rule, okay, with one function being 6xy and the other z. Both of those are functions of x. And then over here, right, was basically just chain rule. And so now, when you do implicit derivatives, you have like a function partial of z with respect to x that you just want to solve for now. And so I've got to go and simplify this thing basically all down. So I'm going to just get this on one side. So I think I'm going to move these two terms to the right. So I'm going to get 3z squared partial of z with respect to x plus 6xy partial of z with respect to x. And then I'm just moving things to the right. So negative of that, negative of that. And then I can factor, this out. And then just divide, and I'd be done. And that's it. Kind of messy looking, but this is the correct way to write the derivative of this thing. Like if you think about how to do the implicit derivative here, you get like a y in the answer, even though you're doing like dy dx. So like you're doing partial z with respect to x, and it's okay that there's a z still. That is kind of like that happens with implicit derivatives.